Nimbus is the world's leading tool for creating fully compliant IVCOM, IVC, and .NET drivers. In this video, you'll see how easy it is to create high-quality Ivy drivers with Nimbus. To begin using Nimbus, we open Microsoft Visual Studio. Nimbus is completely integrated within the Visual Studio IDE so that all phases of driver development, from design and testing to help authoring and installer creation, can all be accomplished without ever leaving Visual Studio. To create a Nimbus driver project, we proceed just as we would with any type of Visual Studio project, by choosing New Project from the File menu. Note that Nimbus includes custom project types for creating new instrument classes, as well as IVCOM drivers. Let's focus on Ivy drivers for now. The first page of the new IVCOM driver wizard allows us to specify basic information about our driver, such as the manufacturer and vendor names, as well as the file names for the .NET driver that Nimbus will automatically create. Of course, these choices can all be changed after we run the wizard, just by using project settings. On the Class Compliant tab, we choose which Ivy instrument class we wish to support. We'll choose Ivy DMM for this demonstration. Next, the LXI tab allows us to include the appropriate LXI methods and properties based on the level of LXI compliance we'd like to provide. For now, we'll choose Class C. The land-based triggering and 1588 timer functionality can all be added later if we like, again, by simply changing a project setting. With the Features page, we have the ability to include a fully compliant IVC driver with our Nimbus project. This really is one of the most powerful and popular features of Nimbus because it allows you to author code one time and get both an IVCOM and an IVC driver. And this really ensures your customers will get a first-class user experience with your driver no matter what AD they choose, be it Visual Studio, where IVCOM drivers work best, or any of the National Instruments tools such as Lab Windows and Test Stand, where IVC drivers really shine. Also, Pacific MindWorks worked very closely with the MathWorks to develop a MATLAB driver feature which automatically generates special MATLAB classes that integrate seamlessly with MATLAB. Nimbus also supports developing native 64-bit Ivy drivers along with dedicated installers for deploying them natively on 64-bit machines. And finally, the help template option allows us to control the look and feel of our driver help file. We'll come back and talk more about help templates a bit later. Let's click Finish and take a look at what Nimbus creates for us. The first thing we see here is the IVCOM Designer. Nimbus already added all of the basic driver functions required, such as initialize and close, self-test, and reset. Note that these functions are grayed out because their definition is fixed by the Ivy specifications and cannot be edited by the driver developer. Since we chose Ivy DMM compliance in the wizard, Nimbus also added all of the methods and properties from the DMM specification. Here we see the configure bandwidth function. Even the standard Ivy DMM errors and warnings are included in our project with the proper Ivy-defined error codes and message string. This allows us to easily report these conditions from our driver when necessary. Notice that Nimbus has even pre-populated the help information for our driver methods and properties based on content taken directly from the Ivy DMM specification. From Solution Explorer, we can access the IVC Designer and see that Nimbus has created a corresponding set of functions and attributes in the IVC driver. Each IVC function typically has a corresponding IVCOM method, and we can navigate back and forth between the two using either context menu commands or by using the convenient info panel located beneath the designer. Most importantly, as we add custom functionality to our driver, Nimbus does all of the heavy lifting required to keep the IVCOM and IVC drivers in sync. Let's see this in action. Let's go to the root of our instrument-specific hierarchy, Acme 4300, and add a calibrate voltage method that takes a few parameters. We'll add a range and resolution parameter, each of type double. And then we'll add a waveform parameter that's an array of doubles, like so. Right away, we see that Nimbus has added a corresponding IVC function of the same name. It automatically added the VI session parameter that all IVC functions need, and it mapped the IVCOM double data type to a VI real 64. And it even knew that arrays in IVC require an additional buffer size parameter to specify the number of elements in the IVC waveform array. In addition to keeping the IVCOM and IVC drivers in sync, Nimbus is managing a lot of source code behind the scenes for us. As we add and remove methods and properties, Nimbus is automatically updating the IVCOM files, like the header and CPP files and the IDL file. The designer allows you to quickly navigate to these source files rather than trolling through files in Solution Explorer, and we can examine the items we've added. Let's check out the IDL file. We see our calibrate voltage method. Then return to the designer, we can look at the CPP file where we would implement our calibrate voltage method as well. There are also IVC driver files Nimbus is automatically managing for us. If we double click on the FP file, or the function panel file, we see that Lab Windows automatically loads with our IVC driver ready to go. If we go and change our calibrate voltage method by renaming it to, let's say, calibrate current, and then delete the waveform parameter, we'll see that Nimbus updates the IVC hierarchy as well as all of the code files. Like the IVCOM header and implementation file, they're updated, and even the IVC function panel file is kept in sync. As we edit our project, Nimbus can validate our design to ensure we're following Ivy rules and to help us eliminate simple errors or omissions. Choose Validate Design from the Nimbus project, and the task list reports any issues. There are several kinds of errors Nimbus checks for, but the only thing reported here is some missing help content, which makes sense because we've not entered any for our calibrate current method. We double-click in the task list and we'll navigate to the offending item. Let's type in some text and then hit enter, and Nimbus automatically updates the task list as we fix things. Don't worry, we'll come back and talk a lot more about this nifty help editor in just a bit, but let's just enter enough text now for the parameters to make the validation happy. We hit enter, and now the task list is clear. Once we've defined a method or property, Nimbus offers a number of features for implementing the item. Message-based devices can be implemented by simply specifying the command to be sent when the method is invoked. For our calibrate current method, the Skippy command for the device might be something like cal, cur, range, resolution. Nimbus generates the code to format the runtime values of these parameters as part of the device command. And there's a lot of flexibility in how commands are formatted, and even a special command editor is available. You can format numbers as decimal, hex, octal. You can specify the field width and precision. Arrays can be automatically formatted as comma-separated ASCII lists, or as IEEE binary blocks, or simply as raw binary. All these options can be incorporated via the designer, and no coding is involved. Of course, for non-message-based devices, we need even more options, and that's what the manual implementation mode is for. In manual mode, you can leverage the Nimbus I/O library for performing direct, low-level I/O using a custom DLL or raw VISA calls or just about any other technique needed. Let's have a look at the frequency max property from the IVDMM spec and see what Nimbus offers in terms of the standard Ivy driver features you may have heard of, such as state caching, simulation, range checking. The simulation editor allows us to manually implement simulation or to have Nimbus automatically implement it for you by either always returning a fixed value or by caching the last value set by the user and returning that value when the property is read. This mode mimics the way we expect most devices to behave, so we'll select that mode for frequency max, as we'll need simulation to be working for the unit testing demo we'll do in a moment. The range checking editor allows us to validate input values against a min and max value or against a set list of values. You can even tell Nimbus which way to coerce or to round a value that falls between two allowed settings. And finally, the state caching editor gives you fine-grained control over which properties are cached. You can enable state caching on a per-property basis, and you can use the couplings editor to manage a list of driver methods and properties that, when set or executed, invalidate the cached value of our frequency max property. Setting up these kinds of couplings is really important to ensure state cache properties always return data that's consistent with the data in the real device. And again, all of these features, state caching, range checking, simulation, and coercion, are all provided without the need to write any code. Let's see how you can use Nimbus to test our Ivy driver. We access the unit test for our IVCOM and IVC drivers from the driver test window docked alongside Solution Explorer. The driver test view manages separate unit tests for the IVCOM and IVC driver so that they may be independently verified. Nimbus uses C# for IVCOM unit tests since it's a very convenient language for accessing COM, while C++ is used in the IVC driver unit tests. Let's have a look at the unit test code for the frequency max property. For the driver test view, we say Open Test to quickly navigate to the unit test code for our property. Nimbus automatically generates code to exercise the property. We'll just change the test value used, and we'll also set a breakpoint. Since we don't have a real instrument here with us, we must run the unit test in simulation mode. Just go to the base test, which initializes the driver unit test, and pass in the IV-defined simulate equals true option. Now we simply choose debug selection on our frequency max property, and we quickly hit the breakpoint in the unit test. We're able to single step through the code and see what's going on. Let's hit continue to let it finish, and we'll see the test results displayed in the driver test results window. To run a group of tests, select the parent node. Nimbus generates complete working implementations of the IV inherent capabilities, so these unit tests will run and pass without modification of the driver or the unit test code. Unit testing the IVC driver works in precisely the same fashion. Select the function or attribute to test, navigate to the test code, set a breakpoint, and execute the test. Documenting drivers can often be as much or more work than building the driver itself. With IV drivers, this is particularly true because you must supply help content that works in Visual Studio, in LabVIEW, and MATLAB. IntelliSense content has to be supplied, and even IVC function panels have their own help formatting content. Nimbus makes it really easy to document drivers because you can use the help editor to enter content once, and that information will automatically appear in numerous places. Nimbus provides a full-featured HTML editor for authoring driver help. Any HTML content, including links and images and media, can easily be incorporated into the driver help file. You can use the Preview tab to see the fully rendered help page with all of the styles and content that we've applied. The look and feel of the driver help file is completely customizable using a special Nimbus feature known as help templates. Nimbus ships with 2 predefined help templates that match the well-known Microsoft styles used in Visual Studio. You can switch between templates to preview how driver help pages will appear for the selected template. For each type of help page, method pages, property pages, etc., you can apply custom fonts and colors, you can add additional sections to a page, you can include additional boilerplate help, and a lot more. And sharing help templates is as easy as copying the template files between driver developers, making it trivial to achieve a uniform look and feel across entire organizations. To create the help file, we simply build the help project. The compilation process actually emits 2 separate help files. One is a standalone .chm file for use in non-Microsoft environments, such as LabVIEW and LabWindows, while the other is an HXS file that's specifically formatted to integrate directly with the Visual Studio help system. Let's see what happens when users write an application with the driver, such as this simple C# application. Users have easy access to the driver help via IntelliSense, or by simply placing the cursor over a driver method and hitting the F1 key to bring up the help page for the selected item. Note how the driver help appears in Visual Studio table of contents right alongside other Visual Studio help topics. Nimbus automatically includes in the driver help file numerous background topics to help end users understand important IV subjects and the basics of working with an IV driver. These topics include plenty of example code, which is automatically created by Nimbus with our specific driver references incorporated. Nimbus even adds topics that give detailed instructions on using your IV driver in various programming environments, from Visual C# and Visual Basic to LabVIEW and MATLAB. If we drill into one of the IV-defined methods, say the configure method from the IVDMM interfaces, we see that Nimbus automatically creates all of the appropriate help information for these methods. This content has been taken directly from the IV specifications. Best of all, these Nimbus help features are managed completely within the Visual Studio environment, without the need to purchase or learn a dedicated package, such as RoboHelp or other specialized help authoring tools. The Ivy specifications lay out more than 50 pages of requirements for building Ivy-compliant driver installers. Let's take a look at how easy Nimbus makes it for us to manage all of these details. Nimbus relies upon an open-source technology known as Windows Installer XML, or Wix for short. Wix is used by Microsoft to build the installers for some of its most important products, such as Visual Studio, Office, and SQL Server. And Wix is ideal for driver development because it exposes the full capabilities of Windows Installer while relying on simple XML source code files that are easy to manipulate by Nimbus, and they're easy to customize by the driver developer. As we edit our project, adding interfaces, methods, and properties, Nimbus automatically updates the Wix source files. Here we'll add an acquisition interface, and returning to the Wix source file, we see that Nimbus has automatically added the appropriate entry for putting our new interface in the system registry. To customize our driver installer, such as deploying additional files or modifying the start menu, we use the Setup Designer, which also manages the Wix source code for us. To add a set of example programs, for instance, just drag and drop the files from Windows Explorer. We click OK and see that the entire hierarchy of folders and files is added to our installer. And of course, you can create new folders, and you can drag and drop to move things around if the arrangement you want on the target machine is different than the hierarchy you have on your local disk. Let's take a peek at all the Wix code Nimbus created for us. Here's our solution file and our Visual Basic form and so forth. Creating the installer is as easy as building the setup project, which runs the Wix compilers on the XML source. The result is a fully compliant Ivy driver installer, without the need to purchase or learn dedicated proprietary installer tools such as InstallShield or Wise. To learn more about Nimbus, visit our website and download a fully functional 30-day trial. And thanks for watching.